He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
The Sun, our closest star, is a massive sphere of hot plasma. At its core, intense pressure squeezes atoms tightly together, forcing them to fuse and release huge amounts of energy. It's a process humans would love to harness for our growing energy needs. But the science and engineering challenges are so immense, it has long floated in the realm of science fiction. But one New Zealand company is giving it a red-hot go. Kia ora, nau mai haramai ki te ao hurihanga. Hello and welcome to Our Changing World. Ko klea Concannon tēnei. This is from a video taken at OpenStar Technologies offices in the Nauranga Gorge just outside Wellington. It's October 2024, and the shouts and claps are coupled with jubilant scenes. Staff are jumping, fist pumping, and sharing handshakes and hugs. They've just achieved a key milestone on their path towards nuclear fusion. Their joy is evident, but what company founder and CEO Dr. Ratu Mataira felt at that moment was relief.
That was the third day of attempts. So first day we really thought we would hit it, and we didn't. And we were live streaming that to investors, our existing investors as well. So by the time you watch the video of first plasma, that's 3 days of very intense work and expectation, and nearly there, on top of 10 months of very grueling work on the part of the team.
We'll get back to first plasma and exactly what that means. But to start, Ratu explains to me the lofty ambition of OpenStar Technologies.
The goal of OpenStar Technologies is to use fusion, both the science and technology of, to unlock limitless, clean, abundant energy for the future of humanity.
Sounds great, right? And we've known how the sun does it and about the theory of nuclear fusion for quite a long time. But the technological difficulties involved in developing an efficient, economical nuclear fusion energy power plant are huge.
But over the last, several decades, and in particular the last decade itself, a lot of breakthroughs have gotten over the line that make us think that there's a pathway to doing this economically, and that really means to the benefit of normal people and making it part of society.
This includes advances in how to make very strong magnets. Because of the promise of nuclear fusion as an energy source, research institutions and governments around the world have been investigating it for quite some time. And there's kind of two main ways people are trying: using powerful lasers or powerful magnets. It was a laser approach that the US Department of Energy's National Ignition Facility used to achieve ignition. That's the term for a fusion reaction that could sustain itself and produce more energy than is put into the experiment. It's a big breakthrough, but how they're currently going about it isn't practical for power plants. One huge international effort on the magnet side, named ITER, involves 35 different nations and is based in the south of France at a massive purpose-built complex. ITER was dreamed up in the 1980s, the collaboration formed in 2006, and construction began in 2010. But last year, the project announced that the reactor wouldn't turn on until 2034, 9 years later than planned. In the meantime, because of the recent science breakthroughs, dozens of private companies have popped up around the world, each hoping to be the first to crack this tricky problem.
Publicly, you can find about 50 companies. There are probably a few more than that. And we all differ for, just like any company in any industry, we all have our kind of unique advantages and our pitch as to why we exist. OpenStar is very unique in building this thing called the levitated dipole, which is a particular way of trying to do fusion. And we think it has a lot of advantages that will mean that we can effectively outcompete the other players in the space. But the interesting thing is that none of us have a product yet. And so we're really competing on our choice of technology and our ability to make that technology work.
Different companies are at different stages. One that's garnered a lot of interest recently is the US-based Commonwealth Fusion Systems, or CFS. In June, they signed an agreement with Google in which the tech giant will take half of the power they create in their planned, but yet to be built, first nuclear fusion power plant.
We've seen very important scientific and engineering breakthroughs from CFS, and we're excited to partner with CFS to take this technology to scale.
CFS hasn't managed ignition yet. They say they're on track for it for 2027. But OpenStar's key point of difference, and why Ratu thinks they have a shot, is the levitated dipole magnet. But before we get to floating magnets, let's start with the basics. And at the nub of it, nuclear fusion is basically about squashing atoms really tightly together.
Something like the sun goes for a really dense gas and crushes it together under gravity.
This is Thomas Berry, Deputy Director of Plasma Science at OpenStar.
And it's still quite hot on like earthly standards, we're talking millions of degrees in the core of the sun, but it's still a few orders of magnitude colder than what we need in a fusion reactor on Earth. And that's because we don't have a massive star providing gravity. So we need to go for the high temperature, lower density approach.
They need to get things hotter than the core of the sun, to about 150 million degrees Celsius. This is where the plasma comes in. Now, it helps here to understand a bit of basic atomic chemistry, the stuff discovered by a Kiwi you may have heard of. When Ernest Rutherford split the atom, he discovered that atoms contain positively charged particles called protons. These are lumped together with neutral particles called neutrons. Around these, kind of whizzing around in an orbit, there's a cloud of negatively charged electrons. And if you heat up a gas sufficiently, the electrons break free, resulting in the fourth state of matter, plasma.
You have these charged particles, so they're influenced by magnetic fields and electric fields, but they sort of move as one, a bit like a fluid does as well.
The sun is a big ball of plasma. Lightning is plasma. We have plasma screen TVs, and neon lights are also plasma. And in the plan for creating efficient nuclear fusion reactions in a lab, plasma is key.
As the plasma gets hotter and hotter and hotter, those ions bounce around and occasionally they collide with each other. And if the speed of that collision, of the particles that are colliding, is just right, they can actually overcome that repulsion force and then stick together. And then once they've stuck together, they then release that amount of energy, which is the fusion process. And that's the energy we capture.
This is the aim. Simple to say, difficult to do. How do you make sure the plasma is purely the gas atoms you want to use? How can you heat it up to such incredible temperatures? How can you prevent it from losing heat? How can you safely contain it? How do you collect the energy once fusion happens? How do you convert this into electricity? And importantly, can you work through all these steps and in the end produce more energy than you've put in? Thomas and I are chatting in one of the meeting rooms alongside the Open Plan office. But it's the massive warehouse beside this space where the real-life testing happens.
So, this is the control room.
Emily Hunter is the lead engineer in Cryogenics and Docking, and she brings me for a tour of the facilities. We start in the control room area, which is this large window overlooking the warehouse, and multiple monitors for readouts during test time.
When we're running an experiment, we'll have physicists and engineers sitting at each of these screens looking at different parameters, and they'll swap out depending on which activity that we're doing in the experiment.
Looking down from above, the warehouse is an impressive sight. Massive shelves stacked with equipment are up against the walls. But it's the 5.2 diameter spaceship-like steel chamber that really draws the eye. When she first joined OpenStar, Emily project managed the chamber's arrival.
So when it was delivered, it actually had a picture of a little alien pilot in one of the nozzles, just printed on paper and printed out because the transport company thought it was funny. It was all lit up, and I like to think that somewhere between Palmerston North and here, some rural resident looked out their window and thought, obviously the government is transporting UFOs.
Down the stairs and with hard hat donned, Emily takes me for a look around. The huge chamber is held up between the ceiling and the floor by massive metal beams. They had to take the roof off to lift it in with a big crane. Within it, they can create a near-perfect vacuum, which they need to run their experiments. But it's not a fast process, says Emily. It takes many hours.
We have the saying, no sleep till pump down. We watch the vacuum pressure tracking on the control room screen, and we eat kebabs and we wait.
So basically you've got 3 different things working away to definitely make sure that there's a vacuum in your chamber. There's nothing in there. And then once that's done, you put stuff back in.
Yeah, so then these skinny silver tubes onto this checker plate, which we can look at from the front, that's the fuel manifold. So what we're looking at here is the fuel puffing manifold. So we have hydrogen deuterium, which at the moment we're not using, and the helium gas flow. These are mass flow controllers, and it means that we can get a very specific mix.
Helium is what they've used so far. It makes sense to test first with it, says Thomas Barry.
Helium is a very safe gas and quite a cheap gas for us to use while we're still commissioning the experiment, basically.
After that, they'll use different isotopes, or different types of hydrogen, one of which is the deuterium Emily mentioned. Hydrogen is the simplest atom, and most of the hydrogen on Earth, we're talking 99.9 something percent here, has just a single proton and electron. And stars can fuse this common version, and other elements too, but only because they're ridiculously massive. Here on Earth, scientists reach for the 2 other types of hydrogen to fuse. Deuterium is one, and tritium is the other. As well as the single proton and electron, deuterium has an extra neutron in the mix, and tritium has 2 extra.
We'll probably pretty soon switch to just using deuterium because it's much more representative and the plasma's slightly higher performance when you switch to deuterium over helium. Tritium you don't want to use until you really have to. It is radioactive, it does decay. It's the heaviest form of hydrogen, and because of that it wants to slowly decay. There's a very short half-life of 12.7 years. But it's still, there's a lot of licensing and regulatory and safety considerations you have to make when you do use tritium, which no fusion company wants to have to deal with until they have to, basically. So you can get a lot of the science done with just deuterium. And deuterium is very abundant in seawater, so it's, in comparison to tritium, very cheap to purchase. Tritium itself at the moment is around $30,000 per gram. So, if you're buying a kilogram, you're talking about $30 million US. So, you don't want to do that until you have to.
So, no tritium for a while yet. Of course, also within this vacuum chamber is the all-important magnet. To get to fusion, you need to constrain the plasma. You need to hold it tight in an area so you can keep adding heat energy and force the atoms together. One way to do this plasma wrangling is by using the magnetic field created by a very powerful electromagnet. The team is in between experiments, so the main magnet is sitting just to the side of the chamber under a sheet of plastic.
This is the core magnet, currently missing its top coil pack.
Special superconducting material has been carefully wound into coils and then assembled into a large layered donut shape.
14 coils of different sizes and diameters that give us the field profile, and is eventually how we can find the plasma.
Superconducting means that an electrical current can move freely through it without energy loss, so you get a really strong magnet. And this magnet is a bit of a diva. It needs accessories. It only achieves its superconducting status to create a powerful magnetic field when it's chilled to about minus 220 degrees Celsius. So it comes with its own cooler box setup. And it's an electromagnet, so it only works when there's an electric current going through it. Therefore, it also needs a power supply. So far, they've been supporting this magnet in tests, so they've been able to plug it in. But ultimately, it needs to levitate inside the chamber, so they've designed systems that will allow the cooling and the powering to happen as it floats.
We use what's called a flux pump as our power supply on board, which is a technology that's been developed really heavily out of the Robinson Institute, just over in Petone.
Victoria University of Wellington's Robinson Research Institute is a well-known name in the superconducting materials space worldwide, because of their research that has enabled today's much stronger magnets. As well as making use of their research findings, several of the OpenStar staff learned their trade at the Institute. For example, Ratu did his PhD there in superconducting magnet technology, and Thomas worked there on plasma thrusters for spacecraft before landing his current job. But back to floating magnets. To levitate the core magnet, they'll use a second superconducting magnet attached to the top of the chamber, one carefully tuned to attract the magnet below by a Goldilocks amount. Enough, but not too much. Other nuclear fusion companies like CFS have gone with a different design, where instead of the plasma surrounding a floating magnet inside a big steel chamber, they've essentially built a chamber out of magnets, and the plasma is contained inside. So where did the idea of a levitated dipole magnet come from? Well, from space, says Ratu, and researchers looking at data sent back from probes going past Jupiter and Uranus.
What those space probes saw were these really big, stable plasmas that had very high pressure peaks in close to the planet. So as you came in from afar, away from the planet, it was kind of a thin, not very pressurized plasma, but the pressure skyrocketed as the probes got in close to the planet itself. And so what he saw was a configuration of plasma that occurs in nature, is stable, and what we like in fusion, a peaked pressure profile. So you can start off at low pressure at the edge, but get a core that is high pressure enough to actually drive fusion. Now, these were all just ideas on paper. The first practical implementation really was this levitated dipole experiment done at MIT. They managed to turn it on in 2004, and they ran it until 2011, when unfortunately the funding was not renewed.
This experiment at MIT in the States used older magnet technology. Ratu has taken the leap of starting a nuclear fusion company in Wellington because of the promise of coupling the floating magnet approach with the new, more powerful superconducting magnets.
What that allows you to do is the plasma that magnet is holding onto no longer touches anything. Once you've removed those mechanical supports that were holding the magnet up, the plasma just is free, just being held onto by the magnetic field, not touching anything physical. And so what you see in the data is that the performance of the plasma skyrockets when you achieve this. So we expect higher temperatures, higher densities of plasma, longer lifetime of plasma, like how long does it stick around for. And all of these things have already been proven out on the plasma side in that experiment that was done at MIT. But this is going to be the first time that anyone's done it with the kind of magnet that we've built using this latest generation of superconductor. And the special thing there is we're not pushing the boundaries on the physics yet, but that magnet technology we're using will go the distance. Like the next one we build will go further than the old technology ever could.
Of course, you don't just go from notes on a page to instant levitating superconducting magnets constraining plasma first try. You have to work in increments. Test, fail, problem solve, tweak, and test again. In a room off the side of the main warehouse area, Emily shows me the magnet workshop, which allows them to build magnets on site. A large metal table with discs, a monitor, and bright orange bobbins sits in front of a big industrial-looking oven.
So, this is our winding table. So we can co-wind 5 strands of superconductor and substrate. We wind it onto big steel and copper bobbins and pump solder between the layers. And then once it's all assembled, we heat it up in that coil oven over there and cool it off. And then we vacuum test it in that bell jar vacuum chamber that we're looking at just now.
So with the vacuum chamber, the hydrogen isotopes as fuel, and the magnet holding the plasma in place, the final ingredient you need for nuclear fusion is heat energy. And lots of it. While they test, the team has an existing heating system that essentially shoots microwaves into the chamber to heat the gas to form plasma. But they're also looking to the future for what they'll need to achieve the 150 million degree temperature to allow fusion. Here's Ratu again.
In the long run, there's a method called ion cyclotron resonance heating. And it's a complicated sounding thing, but basically we take radio transmitters, very similar to what we use for radio stations. So actually, if listeners are tuned into RNZ, that frequency that you've tuned in on is probably pretty close to one of the frequencies that we would fire into the plasma. And once you push those waves into the plasma, they resonate with the particles inside and they heated up. And in that sense, it's very similar to a microwave oven. You're putting in these waves, they're resonating with the particles that you're holding onto in the plasma, and that resonance turns into kinetic energy and turns into heat. And that's what we're needing to add to create the collisions that then drive the fusion reaction. This ICRF process is definitely the best value in the long run, so I think practical fusion reactors are almost definitely going to be using this. But it is also one of the ones that's harder to develop. And so MIT in the United States, and the former home of the last levitated dipole, they also happen to be one of the world's best groups for working on understanding and developing these kinds of heating systems. So we have a collaboration with the team there to develop that for levitated dipoles in particular.
So where are they up to? Well, that first plasma experiment that elicited such celebrations happened on Halloween 2024, which also explains the mystery of why one person is sporting a barbecue grill costume on the video. They reported plasma temperatures of about 300,000 degrees Celsius for 20 seconds. This is a plasma temperature hotter than the surface of the sun, though not the core of the sun, and about 10 times hotter than lightning. For this first plasma, the team used a supported core magnet, their existing heating system, and some helium gas to get plasma up and going in the chamber and constrained by the magnetic field. It was a key test of everything working well. Next step is to do this again, but with a fully levitating magnet. Rumours are that they're close, though Ratu is coy when I ask him about it.
Yes, we are. We're very close. But that's all I'll say about it.
From there, they'll start building and testing the next iterations as needed. So the next version of the magnet, the next vacuum chamber, and the next heating system. As for the bigger picture, if they eventually achieve their goal, the hydrogen atoms will fuse together to create helium, releasing neutrons and a whole lot of energy. What then?
Neutrons don't have any other fate other than to be absorbed by something else or turn into a proton. And so they're flying out of our fusion reaction. They're not being held onto by the magnetic field. And so they can freely fly out, and we have to add shielding and blankets in order to catch them. And they carry about 80% of the energy of the reaction that we're driving. And so if we want to build a practical device, we have to capture that energy from those neutrons. And unfortunately, I don't think there's a particularly clever way of catching it other than letting it hit something and warming that thing up. And so we can't convert that neutron energy directly to electricity. Instead, it converts into heat, and then we take that heat to a steam turbine. And then that steam turbine spins an electric generator, and that's connected to the grid. Now, the sci-fi nerd in me finds this very disappointing. That you do all this amazing work to make a fusion reaction actually work, and then at the end of it is the same steam turbine that has built the modern world. But when you look at what the challenge with decarbonising our grid is, it's finding a power source that looks like what we already have in, say, coal. And it's, you burn the coal, you make the heat, you make the steam, you make the electricity. And so what we're trying to get rid of is the coal part of that, and keep the heat, keep the steam, and keep the electricity. Because so much of what we've built up as an industrial base around the globe is based on that modality of energy. And so fusion is a seemingly very complicated way of replacing that, but the challenge of decarbonising is literally a global scale problem that requires a very high-tech solution in our mind.
And of course, the big question is when? When does Ratu think that we'll have nuclear fusion power plants?
I think the first practical fusion machines will turn on sooner than people think, but that sounds optimistic, but the real challenge is not building the first unit, it's building thousands of them. And so if we think about the goal as decarbonise global energy by the year 2050, we need to bring online an enormous amount of new capacity that's green. And so setting a goal of hitting that first practical machine, say in the early 2030s, is actually a necessary condition to give ourselves the time to then ramp up production, so that through the 30s we're probably learning how to produce them in mass, and then the 40s we're producing them as much as we can, because by 2049 you've got 1 year left and you better have hit that zero carbon goal. And so it needs to be fast. And I think definitely here at OpenStar and among the other fusion companies, we are choosing technologies that we are excited and optimistic and ambitious about being able to hit those timelines, because we have to. And so the prototype that we just built in NZD would have been about 20 million. That's very small fry for a big fusion machine. And it only took us 2 years to build and commission and actually get up and running. And so us in particular, we think that we can effectively catch up to where some of the other concepts are, as long as we can keep moving fast enough and make the progress that we need to.
OpenStar Technologies was founded in 2021. It's a private company backed by venture capital. Today it has close to 60 staff, including one of the MIT researchers that worked on the levitated dipole magnet there, and now splits his life between Boston and Wellington. It's a long shot, but they have a plan, and they think they can do it. And there seems to be a lot of enthusiasm for the mission amongst the staff here. Emily tells me she's pretty sure it's the best job. Thomas says working there feels like a unique opportunity to really make a difference with technology. As for himself, well, Ratu says in his teenage years he would have boldly answered yes to whether he would start a nuclear fusion company.
I had that slapped out of me in undergraduate, and that was the learning that fusion's really hard. And it wasn't until the end of my undergrad and the start of my postgrad where got access to the new technology, was aware of all of the challenges and scale problems of fusion, and saw that that new technology coming to bear was an answer to those things. So I've literally been on the roller coaster. Hopefully it's just up and up from here. But no, I'm an outrageously lucky person to be able to work on something like this.
Thanks to Dr. Ratu Mataira, Thomas Berry, and Emily Hunter of OpenStar Technologies. And thanks also to Elena Pitt and Lenny Ma'iai for their help to organise interviews. This episode was produced by me, Claire Concannon. Production help was from Ellen Rikers, and sound engineering was by Steve Burge. You can find more information and pictures on our webpage. That's rnz.co.nz/OCW. And if you have any feedback or questions, well, you can email us, ourchangingworld@rnz.co.nz. Tēnā koe I whakarongo mai. Thank you so much for listening. I'm Claire Concannon. Have a great week. Kia pai, te wiki.